Apparently there's a leak.
Why C programs leak: manual memory management, the lost pointer trap, complex execution paths, multi-threaded complexity, legacy code bases, non-memory resources. All right, so I wanted to actually demo something live for you. And so we have a C program. It might look complicated. It's not. This function, all it does is it prints a timestamp. Okay, that's so we can see a timestamp here in the console when it runs. This function tries to do something with a file. We'll get to it in a second. That's from here to here. All right. And then we have another function that prints memory usage during the running time of this program. And then we have main, which all C programs start in main. Okay. So the first thing that main does is it prints the timestamp and starting file retry loop. All right. And then it goes into a loop. We've done loops. It prints the timestamp again, and it says attempt to open a file. And then it calls the try process file function. Then it calls the print memory usage function. You get another dashed line. It sleeps for a second. Finally, it says loop finished and a timestamp. Okay. So the main thing is this one here, try process file. I was trying to do a realistic situation. Okay. So in this try process file, the first thing we do, because we're going to read from a file, right? And we're going to grab the contents of the file and put it in memory. So we need memory buffer to hold the contents. So first thing we do is we allocate memory. And notice the early return if we can't get any memory. Nothing wrong with that. We try opening the file. If there's an error, we free the buffer, free the memory, and return early. Okay, and then if we got this far, we would normally assume that we would read the file and do whatever we want to the file and blah, 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 whatever. And then finally, we close the file, and then we also free the buffer, right? Now, what I'm going to do is I'm going to run this. And because of the way this online site works, we only get output after it's done. We don't get to see it live. But let's go ahead and run this, and we'll wait. Okay, so now we have the output. There's our starting output, just like I said. Attempt 1 at trying to open the file. Memory usage, 2,700 bytes. And then the next time, 3,700 bytes. But if you notice, it is pretty steady. I think this is the actual online site that says it doesn't like the fact that our program took 5 seconds. Okay, don't worry about that. Now, that program, there's really nothing wrong with it. Now, let's do this. I'm going to comment this line out. Those are the only 2 free locations. Okay, so we're going to run it again. Now, notice a difference here. 3,700 bytes, 4,700 bytes, 5,700, 6,800, 7,800. We have a leaky program. Now, imagine if that was a long-running program that would run for hours, for days, or whatever. I don't know. Eventually, it would eat up the memory. And you might be saying, Juana, look, just don't write programs in C. Java, JavaScript, Lua, Python, others, they have garbage collection. Or maybe you didn't even know about that.
What is garbage collection? Simply put, garbage collection is the part of your programming language that cleans up after you. See, whenever you create a variable, whether it be an integer, string, or a whole class, your program is allocating space in your computer's memory. This is good while these variables are in use, but once you're done with them, it's the garbage collector's job to go around and remove unused variables from memory. This is in contrast to a language without a garbage collector like C, where you have to unallocate memory manually.
All right, so next time we're going to take a look at a language that has garbage collection, like say, for example, JavaScript, and see if it's immune to memory leaks.